We are really delighted to have Nancy Songer here today to present to us. Of course, Nancy is known to many of us in this room who use her work regularly and build on her work and in their own work. Certainly, Ravit and I and our Praxis team has drawn heavily on all the work that you and your colleagues have done, and so we are very well aware of how much seminal work Nancy has done to lay the groundwork for model-based inquiry and doing inquiry in science classes. Nancy is the Dean of the School of Education at Drexel University and a distinguished university professor. Dr. Songer is an expert in science, technology, engineering, and mathematics, STEM education, with particular emphasis on environmental and biological sciences in urban settings. Prior to being at Drexel, Nancy was a professor at the University of Michigan, where she conducted extensive research with teachers and students within Detroit public schools. And those of you who know her work is aware of how exemplary this work is in terms of really making big changes in the district. And if you're not familiar with this work, by all means, go learn about it. It's really, really interesting. Nancy and her team have developed 8 curricular units focused on complex thinking in environmental and biological science, and 8 apps technology learning tools. Her work has been recognized with several awards and honors and has had impact with over 85,000 students and teachers. So we can all try to aspire to that. Prominent awards include a National Science Foundation Presidential Faculty Fellowship by President William J. Clinton, and the United States of America Department of Education Promising Educational Technology. So Nancy, thank you so much for being here, and we're really looking forward to hearing about conceptual change.
Thank you so much. So I'm delighted to be here. Thank you, Clark, for that very generous invitation, or introduction, I'm sorry. And I'm especially happy to be here because as a dean, I actually don't get to talk about research as much as I would like to, and it's a lot of other important business, as I'm sure many of you can imagine. So this is really the fun stuff for me, so I'm really thrilled to be here and to be talking about work that we've done over the last 5 years, and then some ideas about what we're doing looking forward. So I'm focusing today's talk on conceptual change as kind of the foundation, and the reason for that is that when I was a graduate student, a doc student at University of California, Berkeley, we were studying Rosalind Driver and other foundational researchers that focused on conceptual change. And I feel like it's interesting to take some of the history into account when we're thinking about how we build from prior work and foundational work in my field of science education or other fields that combine disciplines in learning sciences, and then how we go forward, how we build and talk about what's similar to what we're doing now, to what was being done then, and then how we go forward and talk about what new things are happening now and how we need to shift our thinking. So that's kind of what today's all about. This is an overview of the basic ideas. We're going to first talk about what conceptual change is for those that haven't been studying it recently or something. We're going to look at an example of what conceptual change research looks like from Rosalind Driver's team. We're going to talk about what next generation knowledge is, and again, science will be the discipline that will be grounding the discussion, but there's a lot of the ideas here are actually happening in other discipline areas, especially mathematics. Then we're going to talk about whether pedagogical practices are different with a focus on this new kind of knowledge, are misconceptions different with a focus on next generation knowledge, and is assessment different than with a focus on next generation knowledge. And all of you will get a chance to take a stance on those questions as we go forward. So hopefully there will be enough audience participation that you can share in the interactivity section of the talk. So to set the foundation here, Rosalind Driver was a very important researcher in science education. She actually only lived to be 56 years old, but she really had a profound influence on the field of science education. She chronicled children's ideas in science, was one of her and her colleagues' most foundational documents that put together there are all sorts of ideas about what kids' ideas were in heat and temperature and in electricity, motion, and many other of the sort of foundational areas within the science discipline. And so we're going to start with this quote from her book that says, any account of teaching and learning science needs to consider the nature of the knowledge to be taught. So the main idea that and reason why I'm putting this up here is because if we recognize that we're still talking about the same kind of knowledge, same kind of focal knowledge that they were talking about in the 80s or the 90s, then we don't necessarily have to see fundamental shifts in these other things like the misconceptions or alternative conceptions and or assessment, curricula, etc. But if we are recognizing that the kind of knowledge we're talking about now is different, then that causes a shift in all of the other resources that are associated with that knowledge. And so that was an idea that she put forth, of course, and that we're going to be talking about today. So Children's Ideas in Science, as I said, was a place where she chronicled what kids were thinking about electricity, heat, and temperature, Earth as a cosmic body. And that's today we're going to call all of that stuff the target knowledge. That was the target knowledge that her team worked on. She also chronicled the character and persistence of students' misconceptions. And I'm using the word misconceptions here because that's the language that was used in the 80s and 90s by her team. Today we talk a lot about alternative conceptions, alternative ideas, because we don't want to have necessarily this negative connotation that just because there are some faulty aspects of what people's ideas are, they aren't necessarily entirely faulty. Sometimes there's pieces that are accurate, and also we want to be building productively on those alternative ideas. So again, I'm using that word because she championed that term, was one of the people that championed it, but I'm also recognizing that today we don't use that word actually at all, really. Most people talk about alternative ideas or alternative conceptions. And conceptual change was the phrase that was common in the 80s and 90s for what learning is actually happening. The definition I have here is it's the process whereby concepts and relationships between them change over the course of an individual person's lifetime or over the course of history. So one of the things that that her team and others did was they tried to not only look at how learning occurs, but they tried to look at what were the influences and the things that would cause learning to be catalyzed and to be leading to the kind of productive understandings that they were hoping that they would lead to. So here's just an example from the Children's Ideas in Science book, and I know you can't read this, so I'm just going to read this little excerpt with this, this ball bearing spring figure. It says, 2 11-year-old boys, Tim and Ricky, are studying the way a spring extends as they add ball bearings to a polystyrene cup, which is hanging from it. Ricky is intent on adding ball bearings one at a time and measuring the new length of the spring after each addition. Tim is watching him, and then interrupts, wait, what happens if we lift it up? So this was a kind of knowledge that, and a kind of data that Rosalind Driver and others in the 80s and 90s were very well known for, where they would gather these very detailed explanations and transcripts of what kids did under various scenarios. And one of the conclusions was that Rosalind Driver and others would come away with some kind of a summary of what was going on. So in this case, one of the summaries was that Tim believes that weight increases as objects are lifted higher from the Earth's surface, okay? So then she and her team would chronicle these accurate conceptions and or misconceptions and come up with actually extensive documents that teachers and others could use to know about those misconceptions so they could build from it and have more productive learning experiences and better curriculum as time went on. So in Rosalind Driver's words, she said, Tim, like many children, come to science with ideas and interpretations concerning the phenomenon they are studying, even when they have no systematic instruction in these subjects whatsoever. So again, this is an idea that I think is still very true, where we want to be looking at what ideas and interpretations they're bringing, and we want to be talking about how we work with them productively to get to the target knowledge that we care about. So in summary of the whole Driver et al. Team, what they did is they characterized both the correct disciplinary core ideas, and disciplinary core ideas is the term that the next generation science standards use today for the content piece, the disciplinary knowledge content piece of the scientific knowledge. So Driver's group characterized both the correct content knowledge or disciplinary core ideas misconceptions, in other words, incorrect ideas, and how prior ideas are built upon or interact with new ideas, leading to deeper learning. In other words, that learning process or conceptual change. Now we're fast forwarding to where we are today, okay? So today in science, some of you might know, some of you might not know because you're not necessarily doing work specifically in science. There's this whole movement about next generation science knowledge, and it has 3 dimensions to every knowledge piece or statement. I don't know what the right unit is. The 3 pieces are the core ideas or disciplinary core ideas. Again, those are the sort of factual scientific content that, that many of us know as characteristic science knowledge. Something called practices, science or engineering practices. Those are, some people call those also, in the old days it was called inquiry skills. So it's like the how that people do, how you do science. So you might form hypotheses, you might gather data, analyze data, do experiments. Those are all science and engineering practices, and there's 8 of them in the next generation science knowledge. And then there's cross-cutting concepts, which we're not going to talk about a lot. They're big themes in content, and so what happens is these 3 strands must be integrated into one knowledge statement, which they call a performance expectation, in order for you to have the new kind of knowledge, that is the new target knowledge, in the next generation science standards, okay? So I'm not going to obviously go into this detail, but I want to just highlight, maybe, does this have a pointer, I think? Let's see, would that be this? Ooh, okay. So I want to highlight a few pieces of unpacking these knowledge performance expectations. Again, here's the disciplinary core idea in those standards. It's always orange. This one talks about chemical reactions as the content area. Then you've got the science and engineering practices here. Clark and others will be happy that this one's developing and using models. And what you want to do is you want to combine these so that you're actually teaching the disciplinary core idea through the science and engineering practice. And you get this statement up here that integrates or fuses them all into one knowledge statement, okay? So when you combine the colors orange, green, and blue, you get brown. So every time I talk about this fused or integrated performance expectation or statement, knowledge statement, I always use brown text here. And this one says, develop molecular models of reactants and products to support the explanation that atoms and therefore mass are conserved in a chemical reaction. This is a middle school physical science performance expectation. Again, it combines all these different things into one knowledge statement, okay? So that's the new knowledge. That's the target knowledge that we're all working towards, okay? And this is just another way to say that same thing. Disciplinary core ideas in conjunction with and taught through the science and engineering practices. And then here's another example of brown performance expectation that's going to be relevant to the work, the examples I'm showing later. So use a model of the mechanism of the greenhouse effect to construct an explanation about the cause and effect relationship between increased greenhouse gases in the atmosphere and Earth's temperature. And then I underlined the pieces of that statement that refer to the practice, which is using models and constructing explanations. Okay, so now we've said a little bit about what next generation knowledge looks like in those performance expectations. We haven't yet talked about what incorrect next generation knowledge looks like, and we haven't yet talked about what pedagogical practices and learning of next generation knowledge look like. So that's what we're going to switch to now. And here's your first chance to take a stance. Are or should the pedagogical practices be different with an emphasis on next generation knowledge, okay? So what I'm asking you to do is stand up, maybe this is too disruptive, but stand up if you think that the pedagogical practices, based on what you know about what the new next generation knowledge looks like in science, do you think that the pedagogical practices need to be or should be different with an emphasis on this knowledge as opposed to what was going on in Driver's Day, which was just the disciplinary core idea largely that she was focusing on, okay? So does everyone understand? So if you agree, yes, we'll have the yes people stand up, the no people get to sit, okay? So we got this good. I like having some difference in viewpoints. All right, we need a volunteer from the standers to say why you think the pedagogical practices might need to be different. Anyone want to be brave and volunteer an idea? Yes.
Students need to be engaged in these practices in order to be able to meet the performance expectations. So if you've never developed a model or tested it experimentally, how can you do this?
Okay, so it requires more participation in the activities in order to get the understanding of the knowledge. So you think that's going to change or shift the way that pedagogy works, right? Okay, excellent.
Can I just follow up on Eugenia's point? That it really has to be richly intertwined, right? So that it will both inform the students or hone those modeling skills, for example, in the students, but it'll also reveal the kinds of knowledge ontologies that you were talking about.
Okay.
That are different in biology, in physics, and earth science.
All right, excellent. All right, so now the sitters, do any of you, and you guys can sit as well. Do any of you want to share ideas about why you think the pedagogical practices wouldn't be different? And by the way, there's not like a right answer here, so because I'll explain why at the end. Thoughts? No.
I want
Yeah.
the standard, but let me make a case for the,
Okay, good.
for the no. I think if you looked at a lot of the interventions that were being designed, they were in fact rich inquiry interventions. So that many of the activities might actually be very similar or the same. Now, the reason I decided it was more is I think it's the difference. If you're having the classroom conversation and the emphasis is on the concepts,
Right.
you wouldn't have as many step back and let's talk about what kind of reasoning would we do just now.
So that's a really exceptional answer. Not that the other answers we heard in the audience weren't good, but it just shows that these things are very, that there isn't like a yes/no answer. So what Clark said, if I can kind of paraphrase, was that it's not necessarily maybe so much about completely different kinds of pedagogy, but it has something to do with areas of emphasis. And if your target knowledge was disciplinary core idea, just the content part, you might be doing some of these inquiry skills or practices, but you wouldn't be paying as much attention to it or calling it out in quite the same way. This is kind of what you said, right? And so therefore, it actually might end up being the pedagogy might be different, even if or not so different, depending on how big a role that calling out or whatever piece is playing in your instruction. Okay. Yes.
But assessment is definitely different.
Okay. Why would you say that? We're going to get to that later, but I'd love to hear your answer. Why would assessment be different?
Because now, as before, we had the knowledge, disciplinary core ideas, but now we need to assess how they develop practices and whether they understand the cross-cutting concepts. So, and the assessment usually drives what happens in the classroom. As assessment changes, then the teaching method, the learning environment will change just so kids can be successful.
Okay, another excellent answer. You guys, this is perfect. Okay, so that's exactly, I think we'll find more out about that, but it's a good idea to keep in mind that assessment, if your target knowledge has new stuff in it, like practices or learning content through practices, you're probably going to have to change your assessment to gather evidence of how well they're doing on that new thing. So that's great. Okay. So now I'm going to walk through what we've done in our research project over the last, actually a little bit more than 5 years, in 2 different content areas with 2 different target populations, and how, first we're going to talk about what kinds of shifts we implemented for the pedagogical piece of this whole complicated scenario. So the first question that kids were grappling with had a series of activities around which zone of the schoolyard has the greatest biodiversity. And the first thing we did is we had students gather real data using the BioKids app. In the old days, this was actually on those handheld, whatever, Palm Pilot kind of things. Now it's in the App Store. It's called BioKids. It has icon-based entry of, you would go out into a schoolyard, you'd be assigned a region, and you'd have to record information on all of the animals or signs of animals that are in your zone. And then all of the kids' information could be displayed on maps as well as on object-oriented spreadsheet like this that has zone A, C, E along the top. So these are the different groups. These are different groups, and then this is what Zone A saw, and they saw a total of 237 animals of 11 different species. So we were gathering information. This object-oriented spreadsheet helps you to analyze your data and build an argument about which zone, to answer the question, which zone of the schoolyard has the greatest biodiversity, okay? So the pedagogy was fundamentally different here because we had to come up with activities that would have kids practice over and over again, learning about the content of biodiversity through the practices of argument building, data collection, and data analysis, okay? This is just showing you what the screens of the app look like now. It's actually, we also have some new features where you can take a picture and you can get coordinates of the location of your animal. Let's see, so it looks like this, and you observe, you say how you observe it, whether, what kind of a sighting it is, and then these are all animal groups that kids have learned about. And then after you go to animal groups and you pick one, it'll actually list all of the names of the animals that are common in your geographic location. So these apps are organized by geographic location to have the right animals in them. So you don't have like African zebras or whatever, like the original version. And then it's where did you see it and what's it doing, and then they can do some notes and take a picture, okay? So another thing that happened is that it changed the pedagogy, having this new knowledge, changed the pedagogy in terms of what kinds of activities followed other activities. And we realized that it isn't just as simple as having kids go out and collect data, or like come up with a question, collect data, analyze data, and do an explanation. Because there was some of that cycling, but actually what happened over 10 different lessons is this down here says collect data, then this is analyzing data. Then they actually did a fair amount of explanation building around different aspects of the data in order to really have a deep understanding of the data that they were working with. And then they went back and collected some more data, and then they did some more analysis, and they did some more explanation building. So I guess it's a more of a dynamic intersection between the science content and the practices in order to deepen the understanding of the content through the practices. And that was the one of the things that we evolved to in our design of the different curricular units. All right, so we talked a little bit about pedagogy. Now, even though we've already planted the seed about what's going on with assessment, we're going to give you another chance to talk about and take a stance relative to misconceptions and assessment. Okay, so first we're going to talk about misconceptions. Are misconceptions different with this emphasis on next generation knowledge? If you are a yes, you get to stand again. If you're a no, you get to sit. Not a lot of movement.
What do you mean by that?
Misconceptions are the incorrect version of getting to the target knowledge. So if you're focusing on content knowledge and you're talking about gravity, your misconception, or whatever, you have a misconception in how gravity works or how the forces of gravity act on.
So you mean that student difficulty?
Yes. Incorrect answers, student difficulties, those are all under the umbrella of misconceptions.
Right. But incorrect answers as interpreted by us, or we can interpret any incorrect answer, like that boy with a spring who's actually correct if he was talking about gravitational potential energy.
That's correct.
As opposed to wind, right?
That's correct.
So when you use this word misconception, what do you mean?
I'm trying to ask if your target knowledge is now those Brown performance expectations. That's your target knowledge. What does a misconception get on your path to get to that look like? And is that fundamentally different than what a misconception would look like if your target knowledge is just the disciplinary core idea knowledge, okay? And thank you for asking those clarifying questions. So does everyone understand what I'm asking now? Okay, so if you think the misconceptions are different, you get to stand. If you don't, you get to sit. Oh, good, this is good. All right, so a new person who didn't volunteer last time, would you share with us why you think it would be different? And then we'll also ask the seating people for a contribution. Anyone volunteer on why you think it might be different? It's okay. Any answer is a good answer.
It might be different because now we're talking about the practices
Okay.
that people engage in
Okay.
science. So before it was more focused on content.
Okay.
So now students may think scientists start with a certain method, and in reality, it happens in a more chaotic way than expected.
Excellent. Thank you. Do any of the sitting people want to volunteer why you think the misconceptions won't necessarily be different? Very quiet group. Yes, thank you.
Because we don't know the students.
Okay. And it's maybe hard to diagnose, like, or maybe kids have the same kinds of ideas universally, whether in problem areas, and we don't know enough about them to make good judgments. Okay. All right. So you can sit. Just quickly, raise your hand if you think assessment's going to be different, because we already talked about that a little bit. Okay, so I think we actually have we already had a kind of a good discussion on that, and we'll talk about how it might be different. Okay, so the second set of exercises is switching from biodiversity to now we're talking about climate change content as our context. And so even though I know many of you know this, I just put up here some representative kinds of evidence for climate change across different disciplines. And I don't know if anyone's doing work with climate change kinds of curricular activities here. It's an extremely interdisciplinary science, which is why in many ways it's really, really difficult to do. It has many reasons why it's difficult. So anyway, but one of them is because there's evidence in all different areas of science. So the question that kids are working with, and these are older kids now, going up through 11th grade, where do animals live now? And using climate change model data, where do you predict they can live in the future? So actually it's in the year 2100. And what we've done is we've worked with scientists that are part of the Intergovernmental Panel on Climate Change. They gave us these lovely, and I say lovely in a sarcastic way, even though they're very colorful. These are extremely complex formulas. All of these little colors refer to a different formula for what's going to happen to temperature, the surface temperature of the Earth, based on different scenarios, like how much population will grow or not, how many children various people are having or not, how much clean energy people are adopting or not, okay? So based on those different scenarios and formulas, you get these different things which are called futures. The red, the green, the blue, and the pink are different futures. And we tried to work with this, and then even the scientists were saying, hey, our scientists don't even understand these charts. And so we had to do something that we call, which is actually really true, we had to do something called strategic simplification, which means we had to pick out essential pieces of those crazy charts and turn it into a form that kids could use so that they could be working with this IPCC modeled data. And we came up with a plan that has these futures 1, 2, and 3. And under future 1, for example, population growth is fast, but a proportion of clean energy is low. And so the carbon dioxide emissions by the year 2100 in gigatons is going to be relatively large, okay? As opposed to future 3 has a slow population growth, more use of high energy by the population. So the carbon dioxide emissions is going to be lower, okay? So the basic idea is just trying to have some model data and having kids being able to understand roughly what that model data represent. Then we worked with some scientists that have this program that actually maps out where animals live now and where they can live in the year 2100 under different climate change scenarios. So this shows stuff about the red squirrel. The hashed is where the red squirrel lives now in North America. And then this blue is where the red squirrel can live under one of those future scenarios, okay? So we're using this model data and these representations to be able to allow kids to ask questions and make predictions about where animals can be and what kinds of effects climate change might have 85 years from now. So the first pedagogical step was, again, asking the question and getting ready to collect data. The second step here was the same as before, where we have them do the data analysis using these different things. And this is, again, the software interface that we've created, that this is now Future 2 applied to the red squirrel, and the kids can turn these toggle buttons on or off for Futures 1, 2, or 3, and then look at what the relative differences are under those different future scenarios. Then they do pedagogical step 3 again, very much like before, which is argument building and critique, and they're trying to answer this question: is there evidence that climate change will impact the distribution of the red squirrel? And we provide for them that an explanation has 3 parts. This is all stuff that we go over in class. The claim, which is a complete sentence that answers the scientific question, and then they have a field here where they put their claim. Then we define for them what scientific reasoning is, and then they put their reasoning here, which connects the claim to the evidence. And then we talk to them about what is evidence, what makes for good evidence, and they get to put their evidence in this field. And collectively, those 3 fields will constitute their explanation that answers that scientific question. Okay? Okay, so we talked about when we took stances on whether misconceptions were different. I think a majority of the people said no-ish. I think that we were more than that. Okay, and I'm showing you now, even though I know I can't read it, so I'll have to read some of these, some sample misconceptions or alternative ideas that are on this next generation knowledge. Okay, so I'm going to read a couple of these just to give you some examples. The question is, in Future 3, would climate change impact your focal species? Student 2 says, yes, it will impact them. Reasoning, the species distribution decreases because of the Future 3 scenario. And evidence, distribution decreases. Okay, so if we just look at those answers, do we feel like we have some sense of whether these are different kinds of misconceptions than if we had asked students a question just about the content knowledge and not asked them to construct an explanation about their content knowledge? Is that question clear? Mm-hmm. So do you think this is different than what you would have gotten if our focal knowledge was just about, let's say, climate change and didn't have kids developing an explanation about climate change? Any thoughts?
Nancy?
Yes.
So I see how, you've unpacked those, and I think it's really important to unpack those. But with the student data that you have, the reasoning and evidence is still being a little bit, they don't seem that logically distinct. Not that they
That's
should
correct.
be exactly ontologically distinct.
Right.
But when you ask a kid for their evidence, they're really, it seems, my eyes are not very good, but
I know
that they're really just giving you the evidence and the reasoning piece.
That's exactly right. There's a lot of confusion and lack of distinction, and that's very good that you observed that, between what kids have for evidence and what they have for reasoning. Okay, and again, I didn't read multiple answers, but that is a pattern that is common in these kinds of responses. Okay. So does that help us come up with an answer about whether this is a different kind of misconception than what we might have if our target knowledge was just the content knowledge?
Well, what would be the canonical model of what an expert would say for reasoning versus evidence in this case?
So evidence, the way we talk about it, it has to be data-based, right? So you have to draw from, for example, in those cases, those maps to gather information about that. And then the reasoning, as we define it, is usually some kind of underlying scientific concept that links the evidence to the claim. So, but this is a very difficult distinction for a lot of kids. So does that answer your question?
Yeah. Okay.
So what is good is that some kids are getting, for example, that a lot of the evidence pieces say, they're looking at the maps to try to get information. It's in temperate regions, evidence of the model. So these are like trying to draw on the data and information that's in those representations, right? But it's not fully giving us actually what's really good evidence to back this question. So it's only going part way in actually even being able to demonstrate good evidence. And usually in these cases, especially early on, kids' reasoning is also based on the map or is also almost identical to evidence, which again, it's it's hard and it's difficult to get kids to understand that distinction. It's a pretty, it's a, I don't know, it's a kind of a subtle distinction sometimes. So, anyway, so that's what's going on here. I think, is that more an explanation? Okay, so we're going to move on, but hold that thought, because I'm sorry if it was confusing. I'm going to give you a few more types of answers. This is a pre-test versus a post-test to the same kind of question. The pre-test, for example, the first kid says, no. Oh, is there evidence climate change will impact the distribution of the red squirrel? No, where it lives now is close to where it will live in the future. And actually what we have after there is the coding response. So we coded that as a 0, meaning that's not a correct claim there. And post-test, they said, yes, the red squirrel will have to move because of climate change. They will have to move farther north. So that's their claim in both cases, okay? And I'm not showing you other pieces of their responses. But I'm just trying to show you that, that again, these are very complex kinds of knowledge that we're asking kids to construct. And even with a lot of scaffolds and supports, there's a lot of challenges and a lot of different kinds of misconceptions or ways that kids are getting it partially right, but not completely right in these cases, okay? All right, again, we've already taken the stance on assessment. Does anyone want to say anything more about that before we move on? There was some good consensus there. Okay, so Jim Pellegrino, who is kind of my favorite guru in the assessment world, defines assessment as a process that's reasoning from evidence. Okay, so different use of the word evidence here. And because the evidence that we're talking about is what products the kids generate. And what you have to do as a teacher or an assessment person or whatever is you have to draw from that indirect information, that indirect evidence of what somebody knows. You can't physically go into their head and pull out what they know, right? You have to interpret from what they are able to generate on a piece of paper or in an activity or whatever, and that's an indirect form of evidence. So your job is to gather the best assessment evidence you can, and then to do some reasoning or inferencing from that evidence to try to make a valid statement about what the kid knows and doesn't know, okay? So any questions about the definition of assessment before we move on? Okay, so one piece of evidence that we have is actually all of this work now, kids' activities are almost all online except for some experiments that they do. So one piece of evidence we can draw from is how far people get. So this is the first piece of evidence. Is here we have these different kinds of lessons. The teacher can look at, and the students can look at, what percentage of the class has completed this thing. We have 96, 93, whatever percent of the people that have completed. So getting through is actually one piece of evidence, not a very descriptive or deep piece of evidence in terms of how kids are doing, but we definitely want to know if they're even able to get through the assessment materials that we're providing. I'm going to skip that. And now I'm going to actually show you what some assessments are for that biodiversity set of activities that we talked about earlier. So here I'm going to show you a set of 3 tasks that ask 5th grade students to determine which zone of their schoolyard contains the greatest biodiversity. And these tasks, we hope you will agree, provides evidence of both the disciplinary core idea, the cross-cutting concepts, and the practices, and how well they're able to put them together into a coherent product. So the first task is that they go out and collect the data on a number of different animal species. The students are broken into 3 teams, assigned a zone of the schoolyard. So it's very, very similar to what they did in the class activity, but this is now a performance assessment task. The reason why we do assessment in this way and what the purpose is so that teachers can look both at the data provided by individual groups or from the whole class to gauge how well students can perform the scientific practice of planning and carrying out investigations, collecting and recording data in the context of this biodiversity unit. Okay, so it's giving evidence of their ability to do the practices and the content together. And then again, I talked about this before. They're in these teams. They go out, they collect data. Each team is assigned to a zone, and each group gathers and uploads their data, and then it all becomes one class spreadsheet that tells us a lot of information about what's going on for the whole class. The second task is they have to take that data and they have to do a simple version of analysis, which is that they graph the data in bar graphs. And the reason we do this is that the task allows teachers to gauge students' ability to construct and interpret graphs from data, an important element of a scientific practice. Again, so this is all very traditional science kinds of activities, but you can see how if you're looking at it in the performance expectation or the knowledge, it's content plus practices, we're getting information about kids' ability to do both the content, or it shows evidence of what they know about the content, as well as the practices here, doing the bar graph. And then the last task is where they have to construct that explanation that I talked about. And this was our early form of our construction of our explanations before it went to the online form that has the online hints and prompts and that kind of stuff. So this is that we've been working on for several years. So in summary, what we are saying about what next generation assessment tasks need to look like is there are often multiple tasks in a set or bundle that reflect the connected use or the connected demonstration of disciplinary core ideas through a few repeated scientific practices, like we always do, almost always do data collection, data analysis, and explanations as a set like that. We also want these new tasks to address the nature of learning by providing information about where students fall on a continuum between beginning and ending points. We also want to know different kinds of things about, importantly, not just what they get right, but what they get wrong. So all of those little nuances of what they don't know about reasoning versus evidence, or if they don't actually write a full claim and they just say yes as their claim, that's not, that's a form of misconception that's not as terrible as maybe some of the other ones, but clearly doesn't help us provide us with good evidence that they do know and understand what a good claim looks like. Also, a new assessment system would need to include an interpretive system for evaluating a range of student products. So it has to be sensitive to the variations of these right and partially right and things that are good and confused or whatever. And if it can't tease out those pieces about what they're confused about relative to, let's say, evidence and reasoning, then it's not giving us good information that we need. And when we actually have kids do better in that particular area, the assessment needs to be able to pick that up. So it needs to be sensitive to the kinds of alternative conceptions that are common when the knowledge changes to this next generation knowledge, and then provides evidence about it when things get better. So this is, again, another example. I'm just going to show you, I don't want to go into all these details because they are many of the same, but this one does allow teachers actually to have a quick snapshot of like every kid in the class's answer to a particular response, because it's all in these fields. And then this one also gives you, the teacher, a whole bunch of detailed information about one or a small number of kids over multiple times. So they can really even see how the knowledge is growing, or where there are some barriers where things are not being articulated. Like, again, maybe the evidence still isn't being distinguished from the reasoning. Another new piece is that I have a doctoral student named Sonia Zaidi, and she has developed an anonymous peer critique that allows the computer actually to randomly assign another kid's explanation to one kid in the class. So this allows, and then that kid has to critique and provide improvements, if possible, to their peers' explanation as part of the learning experience. And the reason why we did this is because we know that peer critique is a great learning experience, but there's a lot of social dynamics in classrooms that often prevent peer critique from actually working terribly well. Because if kids either popular or not popular or mean or whatever, boy or girl, all sorts of things might go well or not so well. And so this anonymous activity actually has led to some very interesting improvements in kids' abilities to not only diagnose what's good or bad about explanations, but to be able to craft stronger explanations themselves later on. So her results are going to be ready really soon. She's working on a 3-paper dissertation. I don't know if you guys have that here. Okay. I think these are really cool, by the way. So she's working on that. She's got her first paper done, and she should have both the other papers done soon. And it's it's a really interesting complement to some of the work that the larger research project was doing, and it's leading to some exciting results. So in conclusion, we asked the questions, or we tried to ask the questions, is changing the target knowledge change the nature of misconceptions, pedagogical practices, and/or assessment? And I would argue that even though Clark made a really good argument, I think he made a good argument for how maybe one of these areas wasn't necessarily changing, that I think actually all of these are changed and need to change in not terribly subtle ways. Sometimes they're subtle, like the assessment. I think we could see that that obviously needs to provide evidence of practices, but some of the other parts, like maybe the pedagogical practices, that we thought that was more subtle maybe, it didn't need to have a lot of change. But if we're really changing the target knowledge to something fundamentally different and more complicated than what we were focusing on and talking about before, I think every piece of what we're doing, the work we're doing, needs to change to work together as a synergistic unit to respond to that change. So in other words, because the knowledge is different, the alternative conceptions are different, and thus new pedagogical tools and approaches are required. The alternative conceptions include partially fused products, so things that are put together partially well, not so well. Sometimes maybe you would, again, completely understand the claim and what a good claim is, but you're drawing on the wrong scientific information or incorrect scientific information in constructing your claim. So those are the types of errors that we have diagnosed in the same way that Rosalind Franklin's group spent a lot of time in the early years diagnosing what the problems are. And then you want to build your systems to work productively with those errors or those kinds of weaknesses so that you can be sensitive to them and allow everybody to have a greater chance in getting to the correct products. Pedagogical tools should include scaffolds targeting known partially fused products. Again, so you want to have your scaffolds really target the things that you know are going wrong or help with that. And assessment should consist of what we call item sets or bundles. So it's not going to be easy or actually even possible to have, let's say, one assessment task give you all the evidence you need about that really complex brown text performance expectation. That's a really complex piece of knowledge. And so we're finding that the way to get a lot of evidence on that is to actually have multiple questions. Some of them might focus just on a piece of the disciplinary core idea. Other ones would focus on these fused products that have content plus practices in order to get a full picture of the kinds of knowledge and places where kids are doing things that are moving in the correct direction and where they're actually having challenges. I think that's it. Thank you.
Questions? Any questions and comments?
Yeah.
Yeah. Well, thank you, first of all. So on the assessment piece, the way you talked about it here, it felt a little bit like a traditional use of assessment or a summative assessment. And so how do you see that connecting to the point, you raised the point around misconceptions. You randomly answered about the issue that it's not just sort of fixing the misconception, but it's the process, engaging the reasoning process around that that's also evaluated.
Right.
That practices. How do you see that sort of related to the assessment process?
So when you say traditional assessment, can you unpack that?
Traditional purpose.
Oh, purpose.
Not the purpose.
So you mean for accountability purposes?
Of some type, even in a classroom.
Yeah.
It's a summative assessment that did the kids get this thing or not?
I see. So I'm sorry. So can you repeat your question again?
The question, so
I want to make sure I get it right.
So in that purpose,
Yes.
the teacher sort of says, "Oh, these kids learned something or not."
Right.
How well did they do?
Okay.
But how do you think about the connection of the integration of the assessment process into that whole piece around the other components?
Yeah.
So that it's more interactive.
Right.
And supports the other.
So I did talk about using those assessment tasks for summative purposes, evaluation purposes, but actually many of those tasks are used for formative purposes. And because if we design them well, they do provide a lot of rich information about where kids' knowledge is falling short, and we have that information in near or real time. The teacher and or the student has that in near or real time. Then we can definitely use that information to alter instruction or to change the kinds of scaffolds or direction or supports or even conversations we're having in the class around that. And I feel like that's the beauty of actually, if you do the assessments right, that's the beauty of that assessment information, because getting kids to generate an explanation about biodiversity, as I mentioned earlier, is really, really tough, especially when you're talking about kids as young as our case, as 4th grade, 4th through 11th grade. But even the 11th graders, you could see that climate change stuff was crazy complicated, right? So we spend a lot of time trying to make sure that the system has the right kinds of supports. And again, it's thinking a lot about, like what kids are capable of, like kind of zone of proximal development stuff, like what they can do by themselves, what kinds of supports you give them to really stretch them and be able to have them generate rich products that illustrate what they do and most importantly what they don't know, so you can use that for whichever purpose you deem is important for that information, whether it's a formative purpose or a summative purpose. Does that answer your question?
That's helpful. Thank you.
Yeah.
So I think, Nancy, I think this is really great, as you just said again, in helping to scaffold students pay attention to and focus and then hone the practices of, understanding the claim, the evidence, linking it. But what I worry about, what I worry about is the kids who are not good at writing. And so this is my thing lately, because I do so much work with log files, is that the ground truth is really, for these children, these students, limited by how well they can articulate what it is they know. So although the scaffold can help orient them and perhaps draw that out, which is, trust me, very, very important. From a pure assessment point of view, I worry that what's happening is that student knows something that's not getting assessed at all. Yeah. Right? So how do you, this ground truth thing is something that I'm really on about lately, especially because I think the NGSS strands are excellent and rich, but I see that teachers, and I hear from teachers like, oh, thank God you're analyzing log files. Thank God you can give me these performance metrics. Otherwise, I'm trying to figure out what the kids know about, design controlled experiments, etc. Right. So what are your thoughts about that?
So is the question, so I'm not sure, so what are my thoughts about the fact that we're now creating assessments that require so much writing, and how do we work with that?
Yes, and some children are very disadvantaged. Yeah. Now the scaffolding piece is absolutely what we need to do to bring them over the hump. But those kids who are really, especially some of your high math, high science, high mechanical reasoning kids, they're not good at writing. No. I work at, I used to work at a polytechnic up until like 2 weeks ago. These are kids and, I'm like, explain to me what, and they're like, well, I can draw it, I can write you an equation, but words, not so good.
So I think that you have raised a really important problem, because if we're trying to get them to provide demonstrations of this more complex kind of knowledge that fuses the 3 strands, or that is, that's in performance expectation, a multiple choice question is not going to give you the evidence that you want. And so I think that we've raised the bar in terms of what kinds of assessment information we need to really know what they know. But we have to be sensitive to that, is that if they aren't getting, if there isn't good instruction and other pieces in, what the learning, the pedagogical stuff that's guiding them in some of this generation of these kinds of explanation products, then obviously we can't expect them to do well in these kinds of products and have that, we can't hold them to that high standard and expect that we're going to, have the information that we really need. Mm-hmm. So I think the good news, if there is some good news here, even though it's, obviously raising a whole lot of new challenges, the good news is it's forcing us to have better assessment than what we had before, where we could potentially more comfortably anyway rely on multiple choice as giving us all the information that we thought we needed. And now I don't think we have that comfort. So what we have to do, I think, is start younger and having even young kids, and again, this is Common Core has a lot of this kind of stuff going on, like do more writing products, even in disciplinary areas of math and science, so that when they get to Polytech or whatever, they actually do have some, stronger writing skills than they would otherwise have. But in the meantime, it's a huge problem, absolutely. And we don't want to be disadvantaging people for that reason, but that is kind of where we are. Yeah.
Yeah, so when you were presenting your data about the climate change in the squirrel, you had the students try to distinguish between evidence, reasoning, and conclusions.
Or it's claim, evidence, and reasoning.
So something of a simplified Tolman model.
Yes.
Right.
It was based actually on Tolman's earlier models. That's right.
So this model would seem to imply that there's such a thing as pure evidence or pure data that can be distinguished from reasoning. It doesn't require an active interpretation. Wouldn't that be encouraging a misconception about science?
So there are lots of swampy, pieces to everything like this that you're in. I mean, so what I'm saying is absolutely, we are always sensitive to maybe we're introducing a new set of misconceptions rather than really helping. I mean, this is the nature of the work we're doing. And so I won't say the answer is yes, because we've worked on this for many years. And what we try to do is we try to have instructional resources that have very clear distinctions between what we mean by evidence and what we mean by reasoning, because we didn't want going through some of the nuances that Tolman does that we thought were far too muddy for middle school and younger kids to be able to perform on a reasonably well way. And we definitely had a lot of trouble doing the right kind of thing in professional development so teachers could feel comfortable with that too. So we have done a simplification of the Tolman pieces, and I won't say it's necessarily the best, but it's like you have to make some decisions about this kind of stuff, and you have to just try consistent resources so that your kids and your teachers and everybody can work with that to get to the more complicated products that you want them to get to, which is a good explanation.
Yeah, I suppose if you take the learning progression seriously, you kind of have to move through some areas where the students' conceptions aren't quite right to get them to a higher plane as well.
That's right. I mean, and all this depends on, like, there's all of these somewhat, they're not competing completely, but like not all of us in the room, I'm sure, even agree whether claim, evidence, and reasoning is the right 3 categories of an explanation or whatever. The kind of good news is that NGSS very much adopted that same thing that we were doing for lots of years, and so that made our stuff at least work with NGSS performance expectations a lot more easily. But I think these are tricky topics. I don't think we necessarily have the right answer, and there's all sorts of problems. So we work with it and make it the best we can. That's a good question, though. Thank you.
We have time for one more if anybody has a question.
So this is more of a comment. The thing that I worry about for teachers, I think your answer to my question about getting kids writing sooner, fantastic, right? We've moved away from writing, and kids are really poor at writing. Many kids are very poor at it. But I think that, for teachers, we already demand so much of them.
Yeah.
And our ratios are getting poorer and poorer. We're working in a bunch of schools in Oregon in my group, and that the ratio is 50 to 1. Even in kindergarten, 50 kids, 1 teacher.
How's that legal?
Can you imagine? So the thing is, how can you expect a teacher, if we're going to integrate this richly throughout the curriculum in all these content areas, right, so that kids can really hone this skill and deepen the knowledge? Fantastic. How the hell are teachers going to grade this?
Yeah.
I mean, you just...
So I think it's professional development, professional development, professional development. I mean, you have to have, if you really want to do this right, you have to have a whole new, really intensive set of professional development experiences that can help the teachers feel really comfortable in guiding all of this writing, knowing when the claim and evidence and reasoning aren't working well. And we did this pretty successfully in Detroit, but it was really intense. It's a lot of professional development time. We also had, the teachers all were teaching 8-week units, and we didn't want them to be doing anything less than the 8 weeks. And we have graphs that when they only taught, like when there was one study that actually they could pick whether they wanted to do our stuff for the 8 weeks in ecology and biodiversity, or whether they wanted to do the district issued textbook. And we saw this crazy drop off where we could look at, it was like a dose response kind of a thing. We could look at how well their kids did on these explanation assessment items, depending on how many weeks of our program they had used versus how many weeks of the textbook they had used on the same content. And there was like a really crazy drop off. Like the people that did the textbook, because the textbook is going to emphasize and have like end of the textbook quizzes that are all focused on content knowledge largely. And there might be like one question at the end that has them do something like, explain their answer. But it's not the same kind of scaffolding and rich practice with explanation building. And so those kids are not getting all of that multiple experience that allows them to actually be successful on those tasks at the end. So it's a combination of tons of professional development and multiple experiences with these kinds of activities. Like, again, even in the 5th and 6th grade, kids were doing a minimum of 10 different explanation building activities over an 8-week period in order to be able to do well on the final assessments. So when I say that I think pedagogy needs to change, that's what I'm talking about. It's a pretty big change.
Thank you, Nancy.
All right.